Hi, I'm Matt Gaska. I'm an engineer with Siemens. The topic I'm going to cover today is the trace tool in HMI Advanced. So we've got HMI Advanced to start with. Let's go look at the trace tool. Go to the setup area, optimization test, trace, and we get the configuration screen here. Now what we're allowed to do is we're allowed to pull down axes from the column on the left. So in my case, I've got quite a few of them. We're just going to work with X1 for the moment. And then we select which kind of signal we want to get. The thing that I'm going to pick off, that's going to be kind of an easy one to start with, is position actual value measuring system 1. What that means in English is that is the encoder position without any compensations run through all the ball, screw, and gear ratios. So I have an x-axis configured, and we'll go ahead and trace that. Now what I'm going to do is we have to tell it how long do we want to trace this for. I'm just going to say 4 seconds. And when I hit start, it's going to start tracing. See down here that says function triggered, it's running, and it finished. Now I go over to display. And what we get is we get something that looks far beyond too compressed. The reason is I have a motor sitting there not doing anything, so it's just bouncing off of 2 encoder tick marks going back and forth. Now if I wanted to zoom this out a little bit, I can come to scale. And right now, each trace has its own scale. I'm set to auto. So let's say I want to make this range plus or minus 20 thou. I'll add plus 20 thou to my max. Go back to say graph 1, graph 2. And then I can use my up and down arrows to center a trace. So using the up and down arrows on my keyboard, you could be using it on an operator panel as well. Now let's say that I'm doing a trace like this and I say that, hey, this whole graph 2 is just wasting a lot of screen real estate and I could be using this for something useful. That's what this graphics button is for. Hit graph 1, the second one goes away. So let's go back to our measurement and add some more useful things. So let's say I wanted to grab the set point for the position. It's going to be in this list. Position set point. Now what you have to watch for is that some of these variables are going to sound kind of similar. This position set point controller input versus position set point, it's a question of how far in the control loop are they. Position set point is generally going to be the one that's closest to the interpolator, closest to what is generated as a command. Position set point controller input is farther down. That's closer to what's being sent to the drive. It's one of the last things generated. This can be a little bit useful in looking at certain filters and how feed forward is behaving, but in general, position set point controller input is pretty much not useful for most people. I can also get things like my actual value for my velocity, so I can get it off a motor encoder, measuring system 1, or the direct encoder linear scale, measuring system 2. Lots of choices here. The nice thing is there's only maybe 30-40 choices here. This is another favorite, actual velocity active encoder. Then I don't need to think. So maybe 30-40 choices here, and they're all pretty relevant. So I can measure these just like I did before, and take myself out of E-stop, and we'll hit start. And I'll get a bunch of traces this time. I'll get 3 of them instead of 1 because I set up 3 things. You'll notice that my scaling for my first trace stayed fixed. It doesn't update unless you come in here and click to auto. Graph 1, graph 2. So we got something we can see. And so this is kind of boring because it's just something sitting still. Let's do this. Let's try to do a trace from a part program. Now, one of the things about this trigger function is that it always works on trace 1. Whatever axis I'm tracing in trace 1, whatever signal, that's what it's working on. So if I wanted to do it as like a positive edge and I was using encoder velocity, in my first trace. So basically start tracing when I start moving. I can enter a threshold here of like, we'll say 10 inch a minute. As soon as I start moving above 10 inch a minute, we'll start. So I'll hit start on my trace. It's sitting here idling. Let's go look at MDA. Got a little program here that says rapid. We'll comment this out. This is a trace trigger that I'm going to explain later. So rapid to X0, move to X3, end of program. Come in here. It's still sitting waiting. I hit cycle start. Now because I'm moving, my trace triggered based off of moving 10 inch a minute. Okay, now we have something that looks halfway interesting. The problem is that if we look at, let's say we want to look at just the beginning part of this, I'll change my scale of my x-axis. Starting at 0, we'll just go to 500 milliseconds. Graph 1. Kind of lost where I was at 0 inch a minute. Started at 13. One of the things I can do is I can do what's called a pre-trigger. What this means is instead of waiting to trigger until I have the edge rising, I can say that I want to trigger 500 milliseconds before I start moving, before this trigger. So I do that by entering a negative 500. Same thing, or similar thing, of let's say I wanted to wait to start the trace until I was up at the steady state velocity. I could say that that's about 200 milliseconds. I could enter a positive 200 in there to delay the start after the trigger. So we'll do measurement, hit start again, waiting for me to hit cycle start. I run my program, picks up off of that edge. And now this time, what I have is, look at my first second only. What happened this time is that it triggered here at 0 milliseconds because my minus 500 is here. Now one of the things that's a little bit quirky about this is that it was looking for a positive edge. It was looking for a threshold of 10 inch a minute, positive edge, which means even though we're moving very fast in the negative direction, it didn't trigger. It only triggered when we started going positive 10 inch a minute. So you have to watch a little bit and think about this in terms of how you're setting up those. That's the reason I don't use the trace triggers based on reading values as much. I prefer to use trace from part program. Or trigger from part program, sorry. What this is if I go back to my part program, I have this variable, $A trace of an axis equals 1. This is a trigger for the axis that's going to be listed in trace 1. So let's say I had done something like I had set up Y here. I hit start. I run my program. Because I'm triggering for X, this never triggers my trace to run. I'm just sitting here saying started, started, started. It never triggered. I hit reset. Quit my program. Pick my x-axis as the first one again, because that's what I have in my program. I can make y my second. We'll pretend that I changed stuff over here. Oops. Stop my old trace. Start it again. Hit cycle start. This time it picks it up off the trigger in my part program. Now this is good. Now, one of the reasons that we get so picky about using these triggers and needing to be good with them is that we only have a limited number of samples in the trace tool. We only have 2,047 data points. Now that isn't a whole lot. What we can do though is if we want to figure out how much time that is, go into machine data, go to general machine data, search for 10,070. Actually, it's 10,071. Sorry, I lied. And this gives us the EPO time, how fast the main interpolator clock of the NC is running. In my case, this happens to be running at 4 milliseconds. So my maximum trace value that I can do and get good resolution is 2,047 times 4 milliseconds. So 0.0 equals 0.004. It's not going in under decimal here, bummer. But it's going to be a little bit over 8 seconds. About 8,200 milliseconds, give or take. So what this will do is let me run a trace. So I will. And it runs. I get 8 seconds worth of data. I should speed that up for the next round so we don't have to sit and wait for it to finish. And I can come in, and now I have 8 seconds worth of data. So look at graph 1, and let's say that I want to get some good data on this curve because there was something interesting in there. What I'll do is I'll use this function called nextMarkerOn, and I can use my cursor keys to move around the little point on the trace, and it gives me different values. It gives me the value for that point up top here. If I want to do a difference between 2 points, I turn on a second X marker. Again, it starts moving around. You can see my old one that's kind of left here in a lighter pink. And I can see the two of them. Now, one of the things that this does is down here gives me the time difference between the two of them. So it lets me see how far apart they are in time. And what we'll see is that the smallest increment I have here is that 4 millisecond from my interpolator clock. What happens when you start entering larger numbers, like let's say I make this 16,000, which is twice, what will end up happening is when we run a trace, it's running at basically half the sampling rate. It's only sampling every other interpolator cycle. So what ended up happening here is that I ran my program, the trace never started even though I had a trigger on my part program. The trigger occurred on the tick that wasn't being logged. Because let's stop this. I'm just going to say no trigger, start, I'll run my program. Because I hit start with no trigger, that's why I got data. Sorry, this is going to take 16 seconds or so. And what we're going to see here is when I do that same thing with the cursors, I'm only going to be getting a sample every 8 milliseconds. Now, I got 16 seconds worth of data, yay. We will change my scale, and I want to look at the first second so it's a little easier to see. Let's pretend I can type. Graph 1. And bad scaling, sorry. Graph 1. And we'll do the same thing with my X marker. So, X marker off, turn on the first one, I get some point, turn on the second one, I get another point, and if we look at our delta times between the two of them, it's telling us that the smallest unit we have is 8 milliseconds. So when you're setting up a trace, you have to balance out how long of data do you need, like how much time do you need, versus how important is it to get all the high-speed stuff. Because since we're logging at a relatively low rate of 4 millisecond, if we're looking for high-speed stuff like why is an encoder humming, that's usually going to be up in a high frequency, 500, 600, 700 hertz if we're hearing it, maybe 1,000. At 4 milliseconds, that gives us a best, 4 milliseconds is 250 hertz. It's 1 over 0.004, comes out to 250. If we follow all good signal processing theory, that means that we shouldn't count on being able to observe anything above half that, 125 hertz, because of an effect called aliasing, which is basically where signals can hide and show up as different frequencies because you were sampling too slow. So faster sampling is better, but faster sampling means I can only go to 4 milliseconds, and I have limited duration on this. So if we go back, we're going to look at the measurement, and we're going to look at a couple of signals that are useful. The speed coming off an encoder, absolutely useful. Position set point, useful. Position off of each measuring system, very useful. There's another one in here called contour deviation. Let's find it. Sorry, contour deviation and following error. These two are pretty related. What following error is following error is the difference between the command given to the motor or to the axis and the actual position. So that will pick up all of the flavors of servo lag, anything that comes out of the control loops, plus any physical external disturbances. So if you have a rack and pinion, every time you go over a new tooth, you're going to see a minor little blip in the position just from the tooth transfer. That's going to be in your following error because that sees everything. What contour deviation is contour deviation is a similar thing, but at any given velocity, we can do some calculations to come up with a model of what should the following error be. Some of our models are pretty good, some are not so good. So when we're using contour deviation, because that has the following error subtracted from it, it can be very good to look for periodic disturbances. So let's say that I'm looking for something that I think might be a gear-related thing. When I'm looking for that gear-related thing, I'll look at the contour deviation and I'll see that there's a spike every, we'll say, 1,500 milliseconds, second and a half. I can do some math and figure out at the feed rate I was moving, does that correlate to every time I pass a tooth on a rack? If so, that tells me something useful. Because contour deviation is a cleaner signal, it's easier to do things like that. What you can't do with contour deviation is assume that the value that it gives you on the plot is absolutely correct. Sometimes it will be, sometimes it won't. It's kind of not worth learning when it is and isn't. Because the way you use it is you use it to validate, did something I changed make a difference? So let's say you're having a problem with the gearbox and you go out and you get your wrenches and you make a change to the mounting of the gearbox, tighten it up, loosen it up, whichever, and you had run a trace with some contour deviation values, and you see that they improved or got worse. That tells you you did a good thing or you did a bad thing, one of the two. So it's useful as a comparison of the same axis to the same axis. It's not good as a comparison as one axis to another. It's also not a good comparison of when you start making changes to control loops to try to change settling behavior. The control loops are part of the calculation, and as you change those, it'll change the scaling on your contour deviation. There's two other values in here that are extremely useful. Down at the bottom in the drive stuff, there is a value called torque producing current and a value called utilization. Went too far. What these are is two traces. The utilization is a kind of a compound thing. It takes, even though it says M set over M limit, which is M is an abbreviation for current. Sorry, it's an abbreviation for torque. What it actually ends up being is, in a lot of cases, it's a compound of not only the torque limit. Now, this could be how much torque how much current am I using relative to what the motor can put out versus how much current can the drive put out. It'll use the percentage from the lower one, but it'll also be power. It'll also be torque. And it's going to give you the worst case of them. The reason you use this is to figure out if you're running into some kind of limitation where there just isn't enough capacity left in the system to accelerate through some move. Or if you see a trace where you have a case where you're getting contour deviation alarms and you see your contour deviation go up very high, you trace your utilization, you see your utilization flatlined at 100%. That tells you that there's probably some kind of mechanical drag in the system, and there's something that needs to be corrected and you need to go find it. Utilization is a very good value for that. Torque producing current, on the other hand, is useful for different cases. Now, the reason we look at torque producing current and not just total current is because with torque producing current, that's just the current that is used to accelerate the motor or to move through disturbances. You know, if it runs into something, if it's got a problem where you've got a bad bearing and you're needing to draw too much current to move past it. The reason we're not looking at total current is that there are other things that can draw current besides just the torque producing part. For example, with an induction motor, you're going to draw some current just to induce the magnetic field in the induction motor and make it spin. That's not generating torque, but it's still total current, which is why we don't look at it as much as torque producing current. Same thing, certain permanent magnet motors run at higher speeds will also have some current that they use to be able to run above rated frequencies or rated speeds. So in general, without having to do all the thinking, we just look at torque producing current by itself. The other really nice thing about torque producing current is that it has a plus and minus sign. Now, this can be really useful, for example, when you have a vertical axis with no counterbalance. In general, that motor should always have current or torque or current that's only going in one direction. It should always be holding that axis up, because for it to be pushing that vertical axis down, that means that you'd have to be accelerating faster than 1g, which is pretty uncommon. So you can use it for things like that to try to help sort out what's going on in reality. Of now that I have a sign and not just a percentage, you can see more data. Now, all of the stuff that we're looking at in HMI Advanced is available in Powerline or Solution Line. One of the things that is not available in Powerline and is only available in Solution Line is, stop this, this button here that says Drive Trace. What this Drive Trace does is that it allows us to get access to some of the internal drive variables at a much faster frequency. Generally, this will run up to about 8 kilohertz, which is the speed control loop. The limitation is that you can only log signals from one control unit at a time. So, like for example, I'm on my NCU right now, which in my demo system has an X and Y axis. I can select a signal here, and I can pick off something from Y. Where's the rest of my data? We'll go with recommended connections, and so I can pick off, various special speeds. So do I want the speed smooth, speed unsmooth, after various filters, things of this nature. Okay. Now I can add something from X. Get a variable here. But I can't get anything from A or C in this list. The reason I can't get anything from A or C is in my system they're on a different control unit. So I hit abort, go to my next drive device. Oops. Go to my next drive device, which is my NX15. And now out of my NX15, I can see stuff for A and C, but I've lost all my X and Y. So let's go back to X, Y. So that's one of the limitations. This also has a pretty severe time limitation because it has a finite amount of storage space. Now we can see here that we can log at 125 microseconds, so 8 kilohertz. Tells us here that the maximum amount of time I have with these two signals is a little bit over a second. If I take one of these away, set it to nothing, I doubled the amount of time I can take. So as you add more signals, that cuts into how much time you can record. Something I can do to increase the amount of time I can record is to reduce my sampling rate. So a lot of times I'll crank up my sampling rate to 2 milliseconds, so I can get, here I get 30 seconds worth of trace. Now how you make this trade-off depends on what kind of data you're trying to grab. What's more important? Are you trying to grab high-speed stuff, or are you just trying to get at internal drive stuff? It's a trade-off, because this is going to have more variables available to you than what you would have with just the regular NC axis trace. Down at the bottom, we can trigger again, and we can select which signal we're going to trigger on. So again, we can do a positive edge. Do we want to give it some delay after we've reached our threshold? This is our delay, this is our threshold value, that's what TH means. So we can run these as well. Go back to servo trace. Do I want to save data? It's going to ask this a lot. The answer is generally going to be no, because it just wastes time, because what it's doing is it's storing the setup for your trace. So it's up to you, but in general most people don't. Once you have trace data, you have what's a button here that says File Functions. You can save off your trace data as, you can save just the parameters. So let's say that this setup that I've got with X, X, Y, whatever, is something that I'm going to run often. So I can save just this setup so I can call it back quickly, and I don't have to do as much clicking. That's what the save the parameters does. You can save graph 1, just the data off of graph 1, just the data off graph 2, and then if you save this, you can do some more things, and then you can load it back and use it for comparison. So that's good. The other thing you can do is you can save off a picture. These all get stored onto the PCU50 hard drive, and one of the things that I'll do to try to find things is I'll do something like use a very short name like my initials. My initials GSK 111, and I can search the PCU50 hard drive for that if you don't know where you're going to find it. Because the way that I have this set up, it's not going to be real easy for me to give you a path here. But you can move files on and off pretty easily, but more importantly, you can recall them for comparison. So again, let's say you're going to do some test where you want to get the wrenches out, work on something for a while, and then do a comparison of did this get better, did this get worse? You can do that. So let's look at a few more things on the display. So I showed you how the cursors work. One of the things I'll do often is, let's say I want to see what my settling behavior looks like. How does an axis pull into position? Come down here, so I got my position off of an encoder. I hit scale. And what I'll do is, because what I want to see is I want to see something zoomed in pretty tight around here, I'll use my keyboard, Control C to copy, Control V to paste, Control C Charlie, Control V Victor. I'll paste that, press the equals key. I'll say plus, we'll say 5,000. Enter a couple times. And now I have a range that's exactly 5,000. And I can see nice, tight, close stuff. The reason that things like this can be useful is that then every test I do, I'm always scaled the same way, and I can look at things quickly, and I don't have to think and do as much math or as much measuring, because if my scale is always the same, it's easier to read. There are other cases where this might be useful. For example, let's say you're reading torque generating current. One of the things that you can do is you can set your range to, we'll say, maybe plus or minus 30 amps. That way you know you're always centered at 0, and things can be easier to read. So I hope this is a useful video to you, and I hope it helps you, and have a good one.